Okay, great. So I'm very glad to be here. And so we're continuing the discussion of natural language applications. And before I get to that, I want to begin with a little bit of history. So about 70 years ago, in Germany, there was an event called the Nuremberg trials. And this was a very grand logistical challenge because there were judges from 4 nations that spoke 3 languages, English, French, and Russian, and defendants and witnesses who spoke Yiddish, German, Czech, Polish, every language of Europe and Central Asia. And the status quo at the time for translation is that someone would say a complete sentence, then it would be translated. And they did a back-of-the-envelope calculation, and they realized that if they did translation that way, this process would take 15 years. And that was completely unacceptable. And so what happened after that is a process called simultaneous translation, where translators would translate as the person speaking delivered their original sentence. And this led to much shorter delays and allowed for the Nuremberg trials to take place. And this is now the status quo. If you go to any high-level business or diplomatic negotiation or conversation, you're going to see simultaneous translation, not batch translation one at a time. And simultaneous translation is an example of an algorithm that processes text incrementally, 1 word at a time. And I'm going to talk about 2 applications of this process. One is simultaneous machine translation, and the other is a trivia game. And they have this nice structure where you have these predictions, and you need to decide when you're going to trust those predictions. And the underlying machine learning technology that we'll use is reinforcement learning, where you have states and rewards and actions. And for both question answering and machine translation, you have states that are the words that you've seen. You have rewards that are whether you get the translation or answer correct. And then you have actions that the system can take. Do you answer the question? Do you translate the sentence? OK, so I'm going to talk about both of these tasks, but first I'll talk about trivia. Before I dig into that, I want to say, please interrupt me with questions throughout the talk. So if something's unclear or if you have something to interject, just shout. OK, so first, let's talk about Quiz Bowl. So Quiz Bowl is a trivia game that's played in the United States and in the United Kingdom and India, and perhaps other places as well. The way it works is that you have 2 teams facing off against each other, and the moderator reads a question 1 word at a time. And when you know the answer, you hit a button and buzz in. And there are hundreds of teams playing this in the US alone every weekend. So it's easier to tell you what this is by an example. So I'm going to read you a Quiz Bowl question, and when you know the answer, shout it out. And we'll see who the smartest person in the room is. All right, so let's go. With Leo Szilard, he invented a doubly eponymous refrigerator with no moving parts. He did not take interaction with neighbors into account when formulating his theory of heat capacity. So with Debye, he adjusted the theory for low temperatures. His summation convention automatically sums repeated indices in tensor products. His name is attached to the A and B coefficients. Einstein, yes, absolutely right. The rest of the question you can see here. For 10 points, name this German physicist best known for formulating the special and general theories of relativity. So is that Bernhard? OK, so Bernhard is the smartest person in the room, as we knew all along. All right, and so the way the question is structured is that it starts with difficult stuff, so who knows about Einstein's refrigerator, and then getting down to special and general theories of relativity. So I've been giving this talk a number of places. I now have a ranking of universities based on how quickly they answer the question. So Cornell and Colorado School of Mines up the top. I don't know what that means, but these folks know about Einstein's refrigerators. So one question I usually get asked is, isn't this just Jeopardy? And so no, it's not. So IBM recently had their Watson machine that went on Jeopardy and beat Ken Jennings and Brad Rutter. This is not Jeopardy. Jeopardy is not considered a good trivia game by trivia nerds because the way Jeopardy works is you get a whole question. It's shown up on a screen, and then you decide if you want to answer it. So there's still a buzzer involved, but you can't interrupt the question. And so because of that, trivia nerds don't think it's a good test of skill. On the other hand, Quizable is pyramidal. It distinguishes who knows more based on when they answer in the question. So thousands of Quizable questions are written every year. We have some papers at EMLP and in 2012 and 2014 talking about how to create a system that can play this, and I'll go into the details now. So the way we're going to do this is we're going to treat this as a Markov decision process, and you can either buzz now or wait. And the way the system works is it generates a bunch of guesses, and you need to decide which of those guesses you're going to trust, which of those guesses you're going to use. So first, let's talk about the content model which is generating these guesses. And then we'll figure out how to trust it and when to trust it. So what we do is we take a bunch of knowledge from Wikipedia, represent that in a vector space, and then we see when a question comes in what knowledge resources it's close to in this vector space. And we don't want to just use a bag of words representation because the order of words matter. So this man shot Lee Harvey Oswald is very different from Lee Harvey Oswald shot this man. There are two different people being talked about. And so we're going to use recursive neural networks. And so we've heard about recurrent neural networks, and these are two different things. So don't be confused by that. And this was the first time that a learned representation had been applied to question answering using deep networks. All right, so the way this works is that you have a parse tree that represents the syntactic structure of a sentence. And what we do is we're going to map this into a vector space. So how do we do that mapping? So we assume that every word in the sentence has some vector representation. You can start off thinking about this as word2vec or something like that. And we want to build up representations for phrases like this Chinese admiral. But we only have the constituent words. How do we get the representation of that whole phrase? So the way that we're going to do that is we're going to, if there's only a single word in a phrase, we just use that single word. If we have multiple words in a phrase, we need to have some function to combine the representations of the individual words. And we're going to do that recursively. This is why it's a recursive neural network. And the function that we're going to use is just a linear sum of the constituent phrases plus the representation of the word plus some bias term, and then we pass that through a nonlinearity. And this is how we represent entire sentences and phrases. I'll pause here in case there are any questions. All right, so pressing on. And the X's here and the H's, X's represent the word in the phrase, and the H's represent the subphrases. And then this lands somewhere in this multi-dimensional space, and we build this up through all of our words. But, so I've told you how to initialize these representations. You can use word2vec or something like that. And you can randomly initialize the composition matrices, but how do you update these positions? We use something called warp by Weston et al. And so the way this works is you look to see where a sentence lands, and each sentence is associated with its correct answer, and hopefully they're close together. But if there are wrong answers that are nearby, you want to update the embeddings. You want to push the wrong answers away and bring the correct answer closer. And you can backprop through structure to update the embeddings and get a good representation of all of your words. OK. And so now we have a bunch of guesses, but a lot of these guesses are totally wrong, and so you don't want to actually use them in practice. So what we do is we build up a training set of where we get the answers right. We use that as training data to train a classifier where the weights of the classifier are constructed in a way that mimics the rewards that you get from a reinforcement learning system. And so we use a bunch of features. This is easier to see through an example. So let's say you have a question like, this man won the battle. You generate some features from that. What is your distribution over guesses? What's your current guess? How many words have you seen? And the classifier should learn, in situations like this, we get a bad reward, so we should wait. We should take the action of waiting, and let's see some more information before we buzz in. You see some more words. You build up new features. Given your current guesses, you say that you still want to wait. You see some more words. And now things are more confident. You have a strong guess. You've seen a lot of text, and you can answer Julius Caesar as your answer. So we have a payoff matrix that we use to train our weights for this classifier, and we created a little web app for people to play against our system online. It became so popular that we didn't have to pay anybody. People just did it for free, and there are actually 3 bootleg copies of this floating around created by high school students in the US because they liked it so much. So that was a fun way of generating data, very popular. OK, so we can take a look at the embeddings that we get out of this. So here are the presidents of the United States going in clockwise order through time. And so we start with the founding fathers over here, and as you go clockwise in this T-SNE projection, you get to the 20th century presidents down here. And we can see how our system is doing. The recursive neural network is doing better than bag of words representations. One interesting thing is we can't use the recursive neural networks on Wikipedia because the syntax is different. So syntax helps us when our training data are questions, but on Wikipedia the syntax is different enough that it's better to use a bag of words representation still. But we can combine the two and get precision from the recursive representation on questions and use Wikipedia for recall, so that we can get lots of good guesses based on individual words. And we're able to beat about 80% of the people who played our web app, so that's good. So let's see what's happening. So here is a question. He left unfinished a novel whose title character forges his father's signature to get out of school and avoids the draft by feigning desire to join. This is an interesting question because there are no proper nouns. You don't see any places, you don't see any dates, you don't see any of the sort of bag of words features that you would normally use to answer a question like this. Very general things describing a plot, describing the author. And what's interesting about this is we plot the dot products of individual phrases with each of these answers. And so the correct answer is Thomas Mann. And you can see that for the phrase unfinished novel, you have a strong dot product between all of the authors here. And Thomas Mann, Joseph Conrad, and so on, all of these guys have unfinished novels. And so that's good. And so what is it that sets Thomas Mann apart from these other authors? It's this phrase here, feigning desire to join. And so the model is able to learn that when you have an unfinished novel about feigning desire to join, it knows that that is Thomas Mann and is able to answer the question correctly. So this is a success of our algorithm. Let's take a look at a failure instead. So as a young man, this native of Genoa disguised himself as a Muslim to make a pilgrimage to Mecca. Anyone know the answer to this? It's not any of these here. So that is a good guess, but a little earlier than T.E. Lawrence. OK, so it's actually John Cabot, the confusingly named John Cabot. He's actually from Italy. And what's happening here is that you have pilgrimage to Mecca, and Shah Jahan and Muhammad, obviously, and Akbar all made famous pilgrimages to Mecca. And so it's getting that right. But then you have disguised himself, and so it's not learning this very complicated negation of this fact. So it's getting that wrong. OK, so this is all well and good, but how does this actually do when faced off against humans? So we had an exhibition match in May against 4 people who are trivia experts who had been on Jeopardy, and between them all won over $1 million. So in that match, it was actually quite embarrassing. We did well. We tied with the humans, but it ended in a tie of 200 points to 200 points. and we had no provision for a tie. Our system just shut down, and we were unable to resolve the tie. So that was completely inconclusive and a little bit embarrassing. Then just last Friday in Seattle, we played against Ken Jennings. We added in more data, doing some special things to answer country questions correctly. And we were able to beat Ken Jennings 300 to 160 on Friday, and we also have a video of that online. So Quanta versus Ken Jennings, if you want to see that. So that was a lot of fun, but we still need to do better. We haven't played against the very best Quiz Bowl players in the world. We're sort of working our way up to that. These are people who are sort of famous and we're on Jeopardy, but as I said before, Jeopardy and Quiz Bowl are two different tasks. Okay, so there's some other stuff that we're doing using co-reference and using some new deep networks that we presented at ACL last year, or this year, sorry, and incorporating information like story plots. But I'll conclude the first part of my talk with this. Any questions before I move on to simultaneous translation?
Yeah. Okay, so I'm just curious, can you say a little bit more about this reinforcement learning? Do you use this DeepMind method of doing neural network?
Yeah, so it's not back propagating into the deep learning. That's something that that we're working on now, but it hasn't made its way into the system yet. It really complicates training. We're just doing it for the guest generation part at this point, but it's something we want to do, obviously. Nope.
Because my question is the same. So you're updating those coefficients for summation.
Yes, exactly. Yeah. So, but only for selecting the answers. It's not the additional step of doing the reinforcement learning. Yep.
Is there any practical application for this rather than simultaneous translation?
Yeah. So I think so. For instance, detecting bad behavior on social media or chat rooms or things like that. You have words coming in one at a time, especially when minors are involved. You want to sort of detect as soon as possible when bad behavior is going on and filter that out. That's something that we're talking with some colleagues about how to detect that sort of thing as quickly as possible. Yep.
Where from the tree structure of the question comes from? Do you learn it?
No. So we take that as given. We run the that work was in collaboration with Rikard Soka, and so we used his parser to parse the sentences and took that as a given.
Thanks.
Okay. So I'll move on to the next part of the talk: simultaneous translation. So simultaneous translation is really hard. When humans do this, it takes about 3 to 5 years of training after you're already bilingual. So it's not just that you need to know 2 languages, you need to be explicitly trained in this process. It requires also a lot of technological sophistication. There are these complicated rooms with headphones, and so it's not simple and it's not cheap. So why is this so hard? So one reason that it's hard is that many languages are SOV. You have subject first, then object, then verb. And so some examples of that are German and Yiddish. And so Yoda, at least in the original Star Wars, speaks with the verb at the end of the sentence. And this was because Frank Oz spoke Yiddish, the puppeteer of Yoda, and so he created speech patterns that were like Yiddish, which is a Germanic language and has the verb at the end. And so the reason why this is hard is that if you have a sentence like this in German, you have this helper verb in the middle, but the main verb, gefahren, is at the very end. So if you want to translate this into English, you're waiting for this piece of information at the very end of the sentence. And so if you don't guess the verb, you have to wait a long time and introduce a lot of delay in your translation. This is also true for Japanese, and we'll see more about that in a little bit. So we have this paper, Don't Until the Final Verb Wait, trying to figure out when you can guess the verb and do translations. And so the way that we're going to do this is a lot like Google's autocomplete. If you can figure out the verb, you can complete the sentence, and we use language models to do that. And so what we do is we have a bunch of German text, figure out where the verbs are, and then build a language model for each of those verbs. So we build a language model for avanciert, getan, gesperrt, and all German verbs. Or, well, the 150 most common German verbs anyway. And then we can make predictions of the verbs given some input. So we see a string of text, and we always make predictions. So this should remind you of the content model from Quiz Bowl. We're making predictions given some text that's come in. But most of these predictions will be horrible, only around 18% accuracy, and if you just use them naively, you'll get horrible translations. And so we're going to do the same thing that we did before. We're going to build a reinforcement learning framework. We have slightly more complex actions than in Quiz Bowl. So instead of just waiting or answering, you now can just translate what you've seen. Don't predict the verb, but maybe you can translate what you've seen and get a good translation partially out. You can also predict the verb and translate, or you can wait. So these are the actions that you can take. And so let's focus a little bit on the translation system. We're going to assume for the moment that our translation system is a black box. It's German in, English out, and you can't fix your mistakes. So if you commit to a translation where the first word you translate into he in English, and you want to change that to it later, tough luck. So if at a later time you think the translation was it was designed, you're stuck with this first slot being he. So you can't go back and say, oops, I actually meant it. And this is actually fairly consistent with the way simultaneous human translators are trained. You're taught to never admit mistakes when you're doing simultaneous translation. It breaks down the trust between translator and the hearer. And same thing later, if you changed design to renovated, you cannot fix that mistake. And what we're going to do is we're going to take a traditional evaluation metric for translation, BLUE, which correlates well with English and human judgments of translation quality. But we need to make this work over time. So BLUE is just for a single translation, but here we're going to have multiple translations over time, and we need to score them. And the way that we're going to do that is we're going to take a discrete integral of all of our translations. So over time, you have some translations. We'll take the discrete integral to get an overall score. So let's see how this works with a couple of different hypothetical systems. So first, let's start off with a psychic translator. You say one word in German, and then you get the translation out, he went to the store. And that happens to be correct. This is a completely impossible system, but it's a nice comparison to see how the scoring system would work for this. Perfect translation, no delay, and so you get the maximum score possible. OK, so let's look at a more realistic system. Let's look at a monotone translation system where you just translate one word at a time, and it might not look like English, but you can get decent translations, and so this will get a little bit of reward over time, but it won't max out at any point because you made compromises during the translation process. Another thing we can do is batch translation. So this is basically what every existing machine translation system does. You see the entire sentence, you do nothing, you get no reward, then at the end of the sentence you translate it, and you do pretty well, especially on a sentence like this. And then hopefully we can do something that gives us the best of both worlds. For words that are obvious, and we can just translate that immediately, just like monotone, we can get some reward. And hopefully we can do things like predicting the verb at this position and make that translation. And then at the very end, we're doing as well as batch, but like monotone, we're building up incremental rewards as we go. OK, I'll pause here for any questions. OK, so this is a system. We're going to use imitation learning, give it examples of what it should be doing, and try to teach it to follow those examples. But the problem is that the optimal actions that it should take are nearly impossible for our simple system to follow. It's too good of a teacher. It's like learning how to drive when you're 14 from Michael Schumacher. You can't take turns at 200 miles per hour when you can't get out of first gear. So the way that we're going to do this is we have an initial example of things that we should do. We learn a classifier reduction to reinforcement learning from that, and we won't be able to follow a perfect example. So what we do is we interpolate those and get sort of a less good teacher taking turns at 10 miles an hour instead. And so then at some point, we will have interpolated policies, and we get a teacher that we can actually learn from. Our classifier matches that, and we use that as our new policy. So mathematically, this looks like an interpolation between our policies. We flip a coin with probability lambda. Are we taking the perfect policy or our corrupted policy? And after sufficient corruptions, these policies create training examples that our classifier is able to match. And this is called Searching to Learn by my collaborator, Hal Daume and Daniel Marcu. OK, so let's see how this does in practice. We set up a corpora of German news stories. Some are formulaic, some are surprising. A lot of it is from the news. So the things like weather reports are quite formulaic, easy to translate. News stuff is sometimes surprising. We only look at the verb-final sentences. Some sentences in German only have a medial verb, and so we throw those out. We're only interested in cases where the verb comes at the very end, where we can actually do something worthwhile in prediction. So we can look at the overall results at the very end of the sentence. And so we have this optimal policy that we corrupt to create training data. That obviously does the best. Our learned policy does slightly worse than that, as you'd expect. It's not perfect, but it's doing better than batch, and it's doing better than monotone. So this is at the end of the sentence, but we care about the entire time course of the sentence. So how is it doing? So if you look at batch, it does nothing, and then at the very end, it gets a decent answer. Monotone chalks up some early gains, and then falls short of the batch system. Optimal obviously does great all the time. And our learn system lags behind monotone, but then at the end beats both the batch system and the monotone system. So why is that? This is because the German, except for the verb, is a lot like English. You have articles, adjectives, nouns, fairly easy to translate with a monotone system. But the scoring function sometimes penalizes us even when we're doing reasonable things. So here's an example of a sentence. And so we're able to, so this is on older data. So this is when Merkel was not yet chancellor. But we're able to predict that if you have environment minister, the next word is going to be Merkel. So it's able to predict that and do that correctly. And then we predict that the verb is going to be shown. And so blue penalizes us because the actual verb is presented, but shown and presented are really close enough. And ideally, we should get partial credit for that. But blue is a stupid enough evaluation metric that we don't get credit for that. So even though we're making a decent prediction and we're translating it into something reasonable, we get knocked off for not getting the word exactly right. And this is because we're still at the mercy of our translation black box. So what can we do about that to make that better? And so this is a recent paper from Incremental a couple of weeks ago. And what we do there is we're trying to make our machine translation system better. And the way that we're going to do that is we're going to give our machine translation system new training examples that look more like the order in the source language. So in this case, we're not doing German to English, we're doing Japanese to English. And we're going to rearrange the English sentences to look more like the Japanese sentences. And this will hopefully give us a better underlying machine translation system. And so at this point, you should say, but why don't you just use interpretation data? There are simultaneous interpreters out there, you can just use what they're doing as an example. The reason that we don't do that is that, one, simultaneous interpreters are really sensitive about releasing their unedited data. They make mistakes. It's sort of rushed. It's not always grammatical. So they're very, very sensitive about releasing their unedited translations. And so if you're familiar with Europarl or things like that, those have all been carefully edited, even though they were originally simultaneously translated. The other reason is that simultaneous interpreters have to work very fast and very hard. They have limited memory, and so there's actually quite a bit of research that shows that simultaneous interpretation has a smaller vocabulary, has less precise word choice than careful translations when you can sit down with a dictionary and think about what you're doing. Simultaneous interpreters are under a lot of pressure to get out their translations very quickly. So our goal is to do the best of both worlds, get the quality of translations where someone has sat down with a dictionary and carefully thought about what they're translating, and also have word orders that are close to the original Japanese. So what we're going to do is rewrite batch translations to look more like simultaneous interpretation. So we're going to look at 4 different ways of rewriting, and I'll go through an example of each of those. And I'll show you 2 numbers. One is how often you can do this rewrite, and then the percentage of the time that those rewrites lead to a faster translation, that you can get a translation out with less delay. OK, so one thing you can do is you can move quotative verbs to the end. So in news text especially, you have a lot of he said, they announced, yada, yada. So what you can do is you can take those verbs and put them at the end. That's what Japanese does. Another thing you can do is you can passivize sentences. And so you can rewrite a sentence like, we love the new world, as the new world is loved by us. It means the same thing, but this is closer to Japanese word order. The other thing you can do is you can change the order of modifiers of nouns. And so you have the email server of Clinton. You can rewrite that as Clinton's email server. That's more like the Japanese order of modifiers of nouns. You can also move the position of clauses. So we should march because winter is coming. You can rewrite that as winter is coming. Because of this, we should march. So not all of these sound great, but they make the word order closer to that of Japanese. And we measure the delay of this. So if you chunk each of the input sentences, you can see how much delay you have. So in the case of we love the new world, love is at the end of the Japanese sentence because it's a verb-final language. So you have to wait a long time to get that translation out. But if you rewrite it in the passive voice, the new world love, you get less of a delay. So we end up rewriting about 1/3 of the sentences, reducing the delay from around 9 words per segment to around 6 words per segment. And so we end up doing a little bit better, whether you're evaluating on the rewritten sentences or on the original gold sentences. And we can have a range of aggressiveness, how quickly we translate the sentence as it comes in based on the right probability from Fujita et al. And so that's a little bit weird. The translation goes up even if you use the original gold sentences as your reference. That's strange, right? Because you're rewriting these sentences in weird ways, and you're still evaluating with the original gold sentences. Why is the quality not going down? And so the reason for that is that oftentimes when you're translating from Japanese to English, or German to English for that matter, because the verb is so far away from the things that it's modifying, translation systems often just drop the verb completely. And so what's happening is that when you rewrite the sentences like this, you have a greater number of verbs. And so the gold sentences have around 2,700 verbs. And when you use either the gold or the rewritten alone, you get far fewer verbs than using both the gold and the rewritten. So that's what's happening here. If you rewrite sentences in this way, you learn better translation models that keep the verb. Okay, so in the future, what we'd like to do is look at richer translation models, use paraphrase databases to build better ways of rewriting sentences. We just looked at a small number of ways of rewriting these sentences. We'd also like to fit in better reward structures. So there are evaluation metrics for machine translation that look at paraphrases, that look at whether you get the word slightly right, that it's close in meaning rather than just being the exact match. So this is addressing the presented versus shown problem that we had before. And we'd also like to predict the verb through the same sort of syntactic structures that we're using for the question answering bit, not just use sort of flat language models. Okay, so to wrap up, I talked about algorithms that think on their feet. This is the first learned system for simultaneous translation. Previously, all of the approaches had been rule-based. And I also talked about how you can move beyond hand-engineered or bag-of-words features for question answering. One thing that I really like about this line of work is that there's this nice interaction between prediction and confidence, that you're making predictions, and then you need to decide whether to trust those predictions. And I think this is a fundamental problem in machine learning. We often are making predictions from one system, and they get pipelined into another system. Often we accept those as ground truth, but there's underlying uncertainty there. We should be able to use that. And another thing I like about this is that this is an imitation of what humans do. We're looking at how humans play trivia games or how humans translate sentences and trying to imitate what they're doing. And I think that this kind of research helps us understand what humans do and helps inspire us to discover new ways of doing machine learning that mimics human understanding. Just at the very end, I want to mention that I work on other stuff as well. So one thing that I'm interested in is computational social science, looking at how the words that people use reflect their underlying political tendencies. So detecting members of the Tea Party or Republicans versus Democrats, for instance, in America, or liberals versus conservatives in Europe. We also do multilingual topic models, and so this is connecting into the next talk. I also look at interactive machine learning. I talked about that 2 years ago in Moscow, so I decided not to talk about that again. But you're shown something like a topic model, and then you add in input to improve the topic model, similar to the regularized topic models that we heard about before and we'll be hearing about later on today. And I also look at sentiment analysis and internal state. So for instance, trying to predict when people are lying in games such as diplomacy. And we got some nice results here, so that when people become more polite or they change the volume of their email messages or stop talking about the future, they're more likely to betray you in this game called diplomacy. All right, so thank you very much. And I'm happy to answer any remaining questions.
Thank you very much for this very interesting talk. I guess there are some questions.
Yep.
You talked about translation system, how you don't want to, how you don't want to sort of, like you take it as a sort of as a given that you don't want to, once you commit to a translation, you don't want to go back. And I imagine in some cases that makes sense. And I guess example where a different design decision is made is the Google Voice transcription now, where you talk and it's sort of showing you your best guess as it's transcribing, and then as it gets more information, it sort of is going back. And I wonder if you've explored that direction also, or how you would think of it sort of conceptually. Like, do you just always give your best guess, or do you have some penalty for changing your mind a lot?
Yeah, so that's a really great point. So another place where they have updates of translations is the Skype translator, where you see in text form the candidate translations, and then at the very end it gives you a voice output. I think that especially if you're aiming to have voice output, it doesn't make as much sense to correct or to have, like as you suggest, a really large penalty for rewriting. And I think that's the way that we'd like to explore it, to have a very large penalty for rewriting, but I think we need to have user experiments to see how much that annoys people, because it does certainly annoy people and makes you lose trust in your translator.
Okay, so although the talk is very interesting, but we don't have enough time for discussion, so let's move to another speaker.